In this video, I'm going to be covering these topics, and I'll show how to quickly do these in Excel, and then we'll also take a look at the formulas and how to work them out by hand. The main point is that we have two variables, and we're trying to see if they're somehow related. We're hoping that we can find a relationship between them so that we can determine that when there's a change in X, we can predict the change in Y. Let's start with an example from the book. This is on page 208, and it's an example from the game of golf. So we have two variables. Our explanatory variable, X, is going to be the club head speed, how fast in miles per hour we can actually swing the club. And we think there's a relationship between that and the distance the golf ball will actually travel. So you would collect your data on those two variables. And then what we'd like to do first is draw the scatter plot. So on the next page, 209, you can see from the points on the scatter plot that it looks like the faster you swing the club head speed, the farther you go on the x-axis, the higher up the y values are, the farther the golf ball has traveled. So it looks like there is a relationship, and it's the faster you swing the club, the farther the ball will travel. And later in this video, we'll talk about the correlation coefficient to really measure how strong that relationship is. But now I want to focus on this line. Our goal is to draw the least squares regression line. And what that line is, it's the line that is as close to the points as possible. So out of all the lines you could possibly draw, the gaps between the line and these points are minimized as much as we possibly can. And then what you do with that line is you're able to make predictions. So for example, if I went out and swung the club head at 104 miles per hour, I could look at the line and make a prediction of how far my golf ball would go. If I swung it at just 100 miles per hour, I'd go to the line where X is 100 and see what the Y value is and have a prediction of how far my ball would go. So that is the purpose of getting this least squares regression line, is we're trying to map out the relationship between X and Y, and it'll allow us to make predictions. So I'm going to switch over to Excel now and show how to quickly get the scatter plot, quickly get the least squares regression line. And for our example here in Excel, we're going to see how age and metabolism rate are related to each other. And I'm not in the medical field, and these numbers are by no means accurate, but they'll do to serve our purpose and help illustrate the concepts here. And what we would assume is that as the person ages, the metabolism rate is probably going to decline. So let's start by drawing the scatter plot here. So if we select our data and we go up to Insert, Scatter, we can insert a scatter plot. Let me make it a little smaller here so we can fit it in the screen. But Excel just draws the scatter plot for you. And we can see how that data seems to be trending down. The older the person's getting, the dots are getting a little lower. Now, let me move it even more to the center. If you right-click on one of these data points, you can go to add the trend line. And I've expanded my view because my options open up off to the right side of the window. But you want to make sure you've chosen linear so that we're drawing a straight line that's as close to the points as possible, the least squares regression line. And then you also want to display the equation on the chart. And that'll give you the equation of that line. And you can use that equation now to make predictions. So pick any age you want. I'll pick the age 35. What would the estimated metabolism rate for someone who's 35 years old be? Well, based off that line, we just need to enter 35 into the equation for X. So negative 0.6 times X, which is their age. So I'm going to enter 35 and then add 110.2. And so for someone who's 35, we would estimate their metabolism is 89.2. And so two things left to talk about. our residuals and then correlation coefficient. Let's start with residuals. What residuals are going to measure is the difference between our actual recorded data and then the predicted values we get from this line. So let's look at what our predictions would be. So for example, when x is 10, if we plugged a 10 into here, our prediction would be equals negative 0.6 times, and I'll refer to the cell, times A3, which is 10, plus 110.2. So our prediction is 104.2, but our actual measured value is only 102. So there's a little bit of a difference there, and that's what the residual is trying to measure. Now because I used the cell reference for A3, I can just copy this down, and it will do the residual or the prediction for 20, 30, 40, and 50. So we have all our predictions. To find our residual, we're going to just see what the difference is between our recorded data and our prediction. So we're going to do B3 minus D3 for the first one, and copy that down. We get the residuals for each value. Now notice the negative ones mean that the predicted value is bigger than the actual measured value. So this measured value, which would be a point, is actually below the line. That's why we get negative. And for any positive value, it means the point is actually above the line. The actual value is larger than the predicted value. Sometimes you might be asked to find the sum of the squared residuals. All that means is to find the residuals, and then you'll want to square them. So I'll take each value and raise it to the second power, square it. And then if you're finding the sum of the squared residuals, it just means sum those squared values. So the sum then of those squared residuals. Finding the correlation coefficient is pretty easy in Excel, and then I'll explain really what that means. But to do it in Excel, you just need to hit equals to start a formula, and then correl for correlation coefficient. Start your parentheses, and it says it needs two arrays. It needs the two sets of data. So select all the x values, then hit comma, and then select all the y values. And now you can close your parentheses, and it will return the correlation coefficient. Let's look at the textbook for a good explanation of what the correlation coefficient is measuring. So it's always between -1 and +1. +1 means the points are on a perfectly straight upward sloping line. -1 means the points are on a perfectly straight downward sloping line. And so everything in between 1 and -1 for the correlation coefficient is going to be between those two extremes. So if you're close to a +1, you're going to be, the points are going to be close to a straight line sloping up. And then as you get a positive number that's a little farther away from 1, closer to 0, they're still upward sloping, but the line isn't so clear. And then as you get really close to 0, either positive or negative, really close to 0, you can't really even tell where the line would go at all, whether it's upward sloping, downward sloping, etc. And the same with negative. As you're exactly -1, perfectly straight, close to -1, you can tell it's going down, you can see the line. And then here's a negative number that's kind of in between. It's not really close to -1, it's getting closer to 0. You can still tell it's downward sloping, but the line's not as clear. So the correlation coefficient is telling us how strong of a linear relationship exists between the two variables. And it's quick to calculate using Excel. And what we got here was a number really close to -1. So we have a downward sloping linear relationship, and it's pretty strong because -1 is the strongest it can be if all the points were in a straight line, and we have a value very close to -1. So to wrap up this video, I am going to look at the formulas and show how you could figure out some of these values by hand. I'm not going to have time to go into the correlation coefficient formula and how to work that out. If you want to see that email, text me, call me, let me know, and I can send you a separate video for the correlation coefficient. But for the least squared regression line, if you're trying to work that out, you need to find the values for B1, which is the slope, and B0, which is the y-intercept. And I'm on page 210 of the textbook. So for the slope, it says we need that correlation coefficient multiplied by the standard deviation of y divided by the standard deviation of x. So if we came into Excel, I could do standard deviation of x, and here I'll do standard deviation of y, just equals standard deviation of x. And here I need equals standard deviation of y. And the formula said that for that B1 value, we're going to take the correlation coefficient, which I have calculated down there in G12, times the standard deviation of y, so I3, divided by the standard deviation of x, which is H3. And you see we get negative 0.6, which is what Excel told us was the slope when we calculated that earlier. And then to complete the line, we need that y-intercept, and it says we're going to take the mean of y and subtract b1, which is what we just calculated, times the mean of x. So mean of y, mean of x, you'd calculate those, so equals the average of y. And here equals the average of x. And so it said that to get the B0 value, you take y's mean, so the mean of the y values, which is H9, and subtract the B1 value we just calculated, so H6, multiplied by the mean of the x values, which is I9. And you'll get that same value that Excel showed us in the formula. So if you calculate B1 and B0 by hand, you just know that that means your least squares regression line is y equals whatever you get for B1 times x plus, and then the value for B0 goes in at the end. And while working this out, I don't think I explicitly said it, but make sure when you're doing these standard deviations you use .s for sample standard deviation, or you'll get the wrong answer. If you use population standard deviation, the .p formula, your answer will be off slightly.